Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So I reached out to Anatoly Klimov to ask him for his slides for the LENR and detonation in hydrocarbon plasma presentation that he gave, that I did a basic audited AI translation of to the best of my ability. And he came back and gave me the slides, so I'm going to share those with you after this presentation. And also, I asked him, would it be possible to do a replication of it, or to work with him to understand the system better? And he says, thanks for the presentation. I have some remarks on the presentation. He'll send those to me in due course. And he says that the actual MPC EP generator is very complex. And he thinks he can send a simpler variant, and that he'd be happy to work together. And I asked him, maybe the simpler variant would be good, but we can also work on the one that you directly did to do a direct one-for-one replication. And so that's where we left it. But also, Tibby, a MFMP collaborator, has been working with me off his own initiative over the last several days, and he has gone through the paper associated with this, and he has come up with a circuit diagram walkthrough, which I will attempt to give you today. And what we are looking for are for people out there to look over what Tibby has done based on the paper and the assumed mode of operation, for people to come back with feedback, and this is to encourage replication of this device, and hopefully any errors in the interpretation can either be solved by the community or by Anatoly himself. Okay, so this was meant to be presented at an oral session in ICCF 26 in May earlier this year. Unfortunately, he was only offered a poster presentation, and really it doesn't get the credit that it needs to be given the very novel combination of technologies that he's got to solve some of the major problems in LENR. So this is the device operating, and this blob of plasma up here is some of its work product. But the main objectives of this device really was to take a heterogeneous hydrocarbon plasma, as you can see here, and use coherent energy transformations of carbon nanoclusters and hydrogen ions, where those two components are coming from the dissociation of hydrocarbon. And the idea is to replace the expensive alternative of expensive metal nanoclusters, or specially prepared or deuterated metals, and replace those with cheap carbon nanoclusters. Okay, and so it's one of the big problems in LENR, and I actually made this comment myself actually at ICCF 26, that even if you were to get palladium deuterium system working, it's just prohibitive for expensive for most people to have any use for. It's only really a military technology practically, and it's not necessarily, in my view, applicable what you learn in that system to how you would implement it using other forms of fuels. So this is fantastic that potentially it's hydrogen and carbon nanoclusters. This is exactly what the Cooley and Bennett patent that was classified in 1995 was using. If you recall, it was carbon buckyballs, that's C60 nanoclusters that were deuterated, and then these were detonated. And so it's really detonation of hydrogen and carbon nanoclusters, which was in that 1995 patent. And this is rather than having to buy pre-made nanoclusters in the form of buckyballs, what Anatoly Klimov is doing here is he's providing those nanoclusters on demand from erosion plasma, and you're going to see that. Okay, he thinks that he's getting extra thermal energy, and the COP is around about 2 to 4, and he's doing that by detonating energy saturated hydrocarbon plasma. And so that is what he's attempting to achieve here. So he has a list of published papers here, which you can go and look at. They are the list there. And you can see several of these are recent, some not so recent. 2021, this one particularly is 2002, so you can see how long he's been doing this. 2024, 2021. Okay, so the main principle of what he's doing here is, rather than to do calorimetry, is to do what's called explosive shockwave based energy calculation. So this calorimetric method is the most reliable and accurate compared to other known calorimetric methods in any reactors. So like if you're blowing up a piece of dynamite or TNT or those kind of things, or you're doing some sort of explosive process, the shock wave and the intensity of that shock wave is well understood with these kind of formulas to understand the energy that was released in that process. And these are very, very old and well understood processes. So if you achieve a certain shock wave, it must be achieved by a certain amount of energy release, and therefore you get over the problems with calorimetry that's bogged down the field, because people say, well, you're not doing your calibration right, or you're not accounting for this and not accounting for that. If the shock wave's there, the shock wave's there. No one can deny that, and so that's why he chose this particular method. And so here is the overview of the device. We're going to talk about that in a lot more detail with Tibby's work. But essentially, you have an erosive plasmatron, and that's kind of this area of the device. And then you have the magnetoplasma compressor, which is this whole area here. Okay? And basically, stuff comes out of here, and then the electric streamers come in here, and they compress this thing up as it shoots out in this direction. Okay. Now, traditionally, there would have been a snake rather, in the center of here. It would be in this area here. Okay. And the problem is that gets eroded because the plasma is trying to do stuff, and this all gets damaged up here. So the genius of what has been done here by Klimov is he's replaced this central electrode, which is the problem in these processes, with the fuel itself in the place that it needs to be, and in a form of plasma, such that it can take part in the self-organization process rather than be a barrier to it. So it solves so many problems all in one, and it's really novel, and I think he should get a lot of credit for this innovation. So in this particular setup, you can see here is the main part of the device, and this here you can see is the capacitor storage for the main compression. They have a high voltage probe for measuring the high voltages going in there, and then he has pressure transducers here. This one is a microphone, obviously, and this one is a transducer of some type in this tube. And using this one and this one, he can end up by determining the shock wave that's coming out and the timings between the two and so forth. Between the trigger, the shock wave here, and the shock wave there, you can see, how far it's moving and how fast and so forth. Okay, so. Hello, it's me. So step one is basically to modernize the well-known plasma focus device, specifically magnetic plasma compressor. Okay, and this is the thing that is being used by LPP fusion, but they have this same problem of the electrode always dying, and effectively they're doing it by using a heterogeneous plasma cathode. And cathode and anode is a funny thing. It depends where you consider the electricity current to be flowing from. But anyway, I did think this might be anode, but it is cathode initially in the first part of the process and anode and later. But anyway, and the fuel effectively is generated by erosion plasma, and we'll show exactly what that means in a little while. Okay, so the step 2 effectively is, that was the how do we go about solving this problem. The second one is to create an energy-saturated heterogeneous hydrocarbon plasma, and to do that they are using an erosive plasma generator through a capillary discharge, and this allows us to move into what I call the coherent energy transformations, formerly called Lena regime, in the heterogeneous plasma by saturating it with energy, and then taking that highly energetic nanoclusters of carbon and free electrons and hydrogen ions, they are triggering a detonation and very fast electromagnetic compression using the magnetic plasma compressor in plasma focus mode. And so the idea is to accelerate the process of coherent energy transformations, converting that into a detonation state. Okay, so the experimental conditions, the erosion plasma was to be containing hydrogen-containing substances, and so there's several things here. So paraffin is basically, if you have a waxy paraffin, it's essentially just carbon and hydrogen bonded together at various chain lengths. Stearin and C3H8O5, they both contain oxygen. Of course, there's oxygen in the air anyway, and I've argued that oxygen is very important to these processes, so I don't think that's a bad thing. You might want to have something that has oxygen in it if you are to do this into a chamber which is not in open air. So the fuel might depend on the implementation that you want to achieve. You might also want to have this if you were using this as a pulse propulsion in space, for instance. And he talks about the capacity of the storage of the capacitor, and that it can store up to 300 joules, but the typical amount of energy was less than the total energy that was that could be stored. And then he looked at the distance where the different transducers were picking up the shock wave, and so on. And they also calculated that per shot 1.2 milligrams of material was removed from the source, that is to say the source of the hydrogen and the carbon. Okay, so here is your initial heterogeneous plasma, HP, and in this area here, this white blue is the hydrogen. So we know the hydrogen's ions are in the center, which is exactly where we want them to promote the fusion process, because it's a magnetohydrodynamic process, and that will be focusing the things to the center point, the phase singularity of the magnetohydrodynamic structure, and that is where you want your reactants to be. So your hydrogen ion is the most important in that, and obviously that's the most energetic, so that's everything you want is going on there. And then on the outside you have your nanoclusters, and the nanoclusters effectively are the target for your extra electrical energy to be dumped into to encourage the hydrodynamics to go on here as it's folding from the ejection point out to over here. Okay, and you get the plasma focus. It's kind of basically it pinches it in and compresses the plasma as it comes out from the source. And he argues that it's hypersonic, which is very interesting for potentially propulsion technologies. But they observed 2,000 up to 10,000 meters per second. 10,000 meters per second is 22,000 miles an hour. So it's a very, very fast flux of material. Okay. So this is a graph which shows the shock waves for various configurations. And so it's explained there. I'm not going to go into that. The big point here is that based on the calculations of the amount of energy in and the overall energy, extra thermal energy that was released using these shockwave calculations, so in this case it's 100 joules, let's say, in, and let's say 200 joules extra thermal energy, that you have a excess. And given the fact that 1.2 milligrams of materials is removed in the capillary erosion discharge, you can work out that the energy per atom in that amount of material that's removed in that heterogeneous plasma, into that heterogeneous plasma in the erosion discharge, is equivalent to 2 megaelectron volts per atom. And he discusses that this is in line with Parkhomov's 225-day reactor, which actually he didn't believe at the time, but the maths adds up and is in a similar order of magnitude. In fact, very similar per atom. Of course, in the case of Alexander Parkhomov, it's rather expensive and specific. PNKO2, I think it is, Russian-made carbonyl nanostructured nickel, and you have to treat it in a very specific way. You have to heat it up and degas it, and then you have to put hydrogen in there, and the energy of 2.1, I think it was around megaelectron volts per atom, was released over 225 days. In the case of this experiment, it's released in the time it takes for the detonation to occur. So obviously a much higher yield rate. Okay, so where's the energy coming from? He argues that there is transmutation of chemical elements, and he argues that from the point of view that he sees an abundance of lithium, aluminium, calcium, and zinc. Obviously, the zinc you can get from a proton going into the copper. There's copper from the hedgehog of the electrodes in the MPC. The lithium and aluminium and calcium are either going to be fusion fission products or fusion products from combinations of the parts that are nickel, the parts that are copper, and the oxygen and nitrogen in the atmosphere, and of course the carbon and hydrogen. So you can get to these elements readily, and you can go to nanosoft.co.nz and do the calculations. What is surprising is that there are second level ionization of nitrogen and carbon and zinc and calcium, and these have ionization levels of 29, 24, so on, and that is impossible to achieve in a plasma energy that is not exceeding 3 electron volts, which is sort of like in the 20,000s of degrees centigrade. It's impossible for that to occur, and I argued in the previous presentation that that is because it's actually elements coming together that are in a deionized state. And if you do the nuclear calculations with bare protons, they make a new nuclei in the phase singularity in the magnetohydrodynamic system, and then they are emerging in a highly ionized state where there isn't the necessary ridiculous amounts of temperatures to achieve that ordinarily, but it's just because of the way the nuclei is synthesized, it comes out in an ionized state. He didn't offer an explanation for that. I've offered an explanation for that in my previous presentation. Okay, so he also observed potentially, how do we put it here, sodium and silicon and aluminium, and also fluorine. So obviously you've got nitrogen because there's nitrogen in the atmosphere, and there's oxygen in the atmosphere. There's potentially oxygen in the fuel, but fluorine and sodium and silicon and aluminium aren't in any of the components, and so these are other ways of determining synthesis of elements. Okay, so he's pretty sure that there is synthesis going on, and that would be some way that you could account for the excess energy that's being observed. So, conclusion: a unique plasma setup, MPCEP, has been created. It is possible to obtain a stimulated coherent energy transformation and its detonation in heterogeneous plasmoid created by trigger magnetic compressor mechanism in this installation at a static pressure of 1 bar. So he's actually showing that this can be done in standard temperature and pressure, atmospheric pressure. That's very, very useful because a lot of the technologies in this field require special environments, chambers and so forth. This can literally be demonstrated in open air. This heterogeneous plasma consists of cheap carbon nanoclusters and hydrogen ions. Wonderful. Optical spectra have been obtained in the heterogeneous plasma. It was revealed that there are many optical lines of new transmuted chemical elements such as lithium, aluminium, calcium and zinc and their excited states with high excitation energy of about 20 to 40 eV. And I worked out that the third level ionization here, or second level maybe, but I think it's the third level, and I explained how that would occur, would account for 40.1, I think it was, EV of ionization. So really quite amazing data. Intensive soft X-ray with a quantum energy of less than 2 kiloelectron volts. This is typical when you get condensing electron clusters. You get this type of X-ray radiation coming out, but he's also attributing it to these elements being produced. And a flux of low-energy neutrons, which he says in his presentation may actually be fake neutrons. These energy clusters can pose as neutrons. They interact with neutron detectors and so forth, have been detected in HP. The estimated specific release of energy, extrathermal energy, that's extrathermal energy in the heterogeneous plasma, is about 2 MeV per atom. Not over 225 days like the Klimov reactor that I reported in 2019 at ICCF 22 on behalf of Alexander Klimov, but in a fraction of a second in a detonation mode. Okay, so the operation. This is the work that Tibby has done. So this is the overall schematic. This is not in his original presentation. I did include it at the start of my presentation that I gave on the device previously, but this comes from his previous paper, I think from the end of last year. So the explanation is this is the full circuit consisting of 2 parts. There's the erosion plasmatron circuit and the magnetoplasma compressor. Now, at the time, I thought there was another old Russian technology being used, that is to say an Avramenko plug type setup. But actually what was going on is Avramenko was using erosion plasmatron in long-lived plasmoid studies, ball lightning studies. So it might have just been a mistranslation. But the 2 key technologies here is the erosive plasmatron and the magnetoplasma compressor. Okay. So this is the circuit entirely for the erosive plasmatron, and this is the circuit for the magnetoplasma compressor, and we are going to break this down. First up, we have the erosive plasmatron circuit. This has a power supply here rated at 600 volts. It has a supply decoupling capacitor here, and it's listed as 470 microfarads. It has an inrush current limiting inductor. As far as Tibby can calculate, this should be 4 millihenries. And he has a discharge energy storage capacitor. This is the big boy. And at least rather at this level, and to be announced. He then has this high voltage pulse transformer, and this is the trigger to release the energy that's stored in here. And there's a spark gap effectively that's generated between the nickel anode. So this is you can actually look at it. It looks like a bit of ready rod in the back of his diagrams. So it may be nickel, or it may be nickel coated, or he may have chosen a nickel thing at the head here, but he's saying it's a nickel anode for the erosive plasmatron circuit. And then this piece here, and we're going to look at a close-up in a little while, this is the copper cathode, effectively, of the erosive plasmatron circuit. So here we go. And the actual erosive plasmatron and spark occurs in this area, and we're going to have a closer look at that. So here we go. So you have the copper cathode here. It's this bit here, and the anode here of nickel. And so you have the discharge that goes between the cathode and the anode, and because it's a current flow and it's a plasma, it's going to have vorticity in there. It's also going to create shockwave in there, and also it's going to create a big expansion of the gases that are in the volume of the capillary. So the discharge will cause a large expansion of the gases. This and the energy in there will be causing the plasma to erode the material on the side here, which he argues is PMMA. This is a carbon, hydrogen, oxygen plastic. And as this comes out, you've got the helicity, the vorticity that's introduced by the plasma in an electric current discharge, and that's around the discharge channel. Then as the gas is coming out of here, you will have the helicity, the vorticity, the shear, the hydrodynamic shear in the orthogonal plane. And so you've got multi-axis hydrodynamic shear in a plasma and nanoparticle and ion environment. This will create the conditions for producing a stream of energy soliton type structures, magnetohydrodynamic plasma structures coming out of here. And it would appear from the videos that I would imagine the electrons, just as in the Armstrong electrostatic boiler, and the protons are focused into the center of the highly energy rich saturated nanoparticles and plasma and protons that are coming out of here. Okay, so you can see here, this is the anode, and that's the cathode, and then you have the capillary tube here. That's the edge of the capillary tube, and then here we have our discharge path, and it's going in, discharging, and then that basically concludes the circuit for the erosive plasmatron circuit. So it's really quite simple, it would seem. Of course, the devil is in the detail. And we will go on to the magnetoplasma compressor MPC circuit here, which is, as shown before, the outline here. The power supply voltage source is this 2 to 4,000 volt source. It has this 10 kilo ohm resistor to limit the current rushing in, and then it has the storage capacitor. That's, I think, the big brown one we saw in the images earlier, 100 microfarads. And that is where the main energy is stored that will be dumped into the MPC later. And then it has this triggered spark gap. So basically this can be charged up, but because the gap here is too much of a dielectric barrier for it to discharge at the voltage that this receives over this distance, it needs a triggering mechanism to start some plasma so that the conduction is initiated to allow the dumping of the power into the MPC hedgehog spikes. This is a pull-down resistor, and this is a current monitoring shunt resistor, so you can know what current is going in. And this here, what was the copper cathode for the erosive plasmatron circuit, now becomes the copper anode for the magnetoplasma compressor circuit. And so this allows this one all around here to be the source of the heterogeneous plasma jet, which is the anode, the gaseous anode for the magnetoplasma compressor. Okay, and this is the huge innovation that he has done. And the copper hedgehog spikes here, as it's called by the inventor, is a copper rod cathode of which is the part of the magnetoplasma compressor circuit. So this becomes the cathode. This is the anode, and the anode will connect to this inner electrode that formerly was the cathode of the erosive plasma circuit, but now becomes the anode of the MPC circuit. Okay, so that is that concluded, and so we'll go through the circuit operation. So basically, for the erosive plasma circuit operation, the voltage source with its decoupling capacitor through the inrush current limiting inductor charges and primes the discharge energy storage capacitor. And you can see the current flow in that part of the circuit. Obviously, you've got the grounding here. Then the result is that the EP discharge capacitor is primed, ready to go. But it's not going to go until we trigger it with the spark gap, which is in here. Okay, so you've got to trigger that, and the way we do that is we have this high voltage pulse transformer, and you excite that primary with high voltage, high frequency pulse, and this causes the secondary here to emit an even higher voltage pulse, and then that enables a pulse that is high enough voltage to discharge between these two cathode and anode in this case, and that produces a conduction path. And when that conduction path is then in place, this allows a conductive path through here. That is when the major power from the capacitor for the erosion plasma discharge through the capillary tube is allowed to go through, and so the result is that the capillary tube area has conductive ions and current can flow. So with the conductive ions in the capillary tube, the erosion plasma energy storage capacitor can discharge its array through this current path here. So essentially you've got a triggered release of the power here, but you have this high voltage pulse to create the discharge channel through which it can work. So the long duration voltage applied to the secondary quickly saturates the magnetic core of the transformer. The winding loses its inductance. With minimal loop inductance, the current will rise to hundreds or thousands of amperes. The capacitor will drop to zero. The capacitor voltage will drop to zero. However, due to the loop inductances, it can oscillate, leading to negative voltage. The inductor here limits current flow from the power supply and bypasses the cap, and the power supply over here is safe. So it's a very clever circuit. This is Tibby's best understanding of how this will work, and it's really rather clever. Okay, so there we go. Most of the voltage drop is across the spark gap, meaning most of the dissipated energy is inside the capillary tube. The plasma inside the capillary tube will erode the walls and expand, shooting out a heterogeneous jet in this direction. Okay, with the vorticity that way and vorticity that way. Okay, producing multi-axis hydrodynamic shear into a jet. Okay, so essentially that is pretty much that done. Erosive plasmatron circuit is summary. The prime energy storage capacitor, firstly, there's a trigger by a high voltage ionization of gas in the capillary tube, and this allows for the discharge energy storage capacitor to obtain heterogeneous plasma jet from the capillary tube. Okay, so on to the magnetoplasma compressor circuit operation. Firstly, there's the voltage source we talked about earlier. This goes through the current limiting resistor and charges this big fat brown 100 microfarad capacitor. Okay, now that's the current path for that to do that. So the voltage source through the current limiting resistor charges and primes the discharge energy storage capacitor. And there we go. The voltage is sufficient to jump. The voltage is insufficient, rather, to jump the triggered spark gap. So that's across there. It's insufficient to jump that at this stage. Although the MPC discharge area can have conductive plasma due to the previous EP operation. So yeah, it might have conductive plasma up here, but we don't have a means by which to dump power into that plasma and do the magnetoplasma compression. Okay, so using the start generator, the center trigger electrode is high voltage biased at the proper time delay from the EP gas anode formation. So at the point, so what Anatoly said is that after you've produced the initiation of the heterogeneous plasma here, there is an important time delay that you must leave, and I guess it's from between well, it has to get out far enough so that there is a path for it to discharge through and that this circuit's done its work. Okay, the center trigger electrode, a high voltage biased at the proper time delay from the erosion plasma gas anode formation, and this causes ionization here between the center trigger electrode and one of the high current electrodes. Okay, and so we get a bit of a discharge here, and then what that allows is for a shorter, you're going to have some conductive ions in this environment here. That is to say, with ions in the vicinity of the high current electrodes inside the trigger spark gap device. This allows, and there's ions here, okay, so you've got ions here and ions here, ions between the magnetoplasma compressor, anode and cathode. The energy storage capacitor will discharge. So this big fat 100 microfarad capacitor here can come all the way through here, through here, through here, and into the erosion plasma, this energy saturated, which is effectively the anode for the MPC. Okay, so you can see how well thought through this is, and obviously Tibby's done a fantastic job of this walkthrough. Okay, so you can see this power goes through there, back through there, through there, back through there, until the capacitor is discharged. The energy storage capacitor will discharge. Okay, magnetoplasma compressor circuit operation. Current levels can rise to thousands of amps levels. Magnetic compression of the plasma can occur, leading to plasmoid formation. Now, I've argued that there's already loads of little plasmoids coming out of this multi-axis shear hydrodynamic generator of fuel that then becomes the anode. So there's a whole stream of these things coming out here, but they are then more self-organized without the restriction of the old type of MPC's central snake electrode. There's nothing getting in the way except the things that you want to become the fuel, right? And so it's really rather genius. And so effectively the magnetoplasma compressor MPC circuit works like this. The primary energy storage capacitor you prime the energy storage capacitor, this one with your power here. You activate the spark gap switch when the gaseous anode is ready. So you need to do your erosion plasma here, and then when that's ready, you activate this here, and that allows for the discharge to come through here, and the discharge storage capacitor to obtain high current and magnetic compression of the plasma, and you get your thing going around and whatever. Okay, all right. So I think that essentially is about that, and I want to thank Tibby for doing this. I want to thank Anatoly Klimov for sending the original slide deck over. I will send this out and you will all have it. So thank you very much for your time, and I will see you in the next video.